Hello and welcome to the Engineering Dynamics Course Companion. This is class 12. This is the last Kinetics of Particles class. We'll be switching to Kinematics of Rigid Bodies in the next class, in class 13. Today we're going to cover Oblique Impact of Particles. As always, you could go to the table of contents below and jump to the example. But we'll start with the bottom line up front. All right, so Oblique Impact uses a normal coordinate that is aligned with the center of the particles and a tangential coordinate which is perpendicular to that normal coordinate axis. That definition allows us to take in the normal direction, treat it just like it's a central impact, just like we had in the previous class, and in the tangential direction, the velocity of each particle actually remains the same. So we'll discuss that. And conservation of momentum is how we apply to this thing. We apply it in the normal direction as if it were a direct impact problem. And we also use the coefficient of restitution again, but this time we add in this little subscript n to indicate that it's being used in the normal direction. So oblique impact, right, is like direct. Well, okay, so here's direct, right? So that's the one we just covered in class 11. But now we have oblique, right? So the two particles, they're not aligned with each other. They're coming at the centers of them are pushed down. So where they're hitting isn't directly into there. They're moving like this right here. So you can think of that as pool-like balls, but like cutting in the cue ball to cut another ball to send it into a different direction, right? And we also the velocities might not be aligned, right? So they might be coming at each other. They aren't necessarily coming here in offset. They could be coming at weird angles to each other, as they're hitting, right? So we define this line of impact as being through the center of the balls, right? So that's the best way to try to approach and figure out where that is going to be. And we define that as the normal axis. And we have a tangential one that is going to be perpendicular to it. So that's an important thing an important first step when you're trying to figure this out, is to create that coordinate axis onto the thing. And then for whatever velocity that the thing has, you want to break the velocity into those components, right? So you want to try to figure out what those angles are. So you can see how along this line of impact is actually a direct central impact of these two pieces. And then, so we draw out the impulse momentum diagram right here when there's two particles. Because there's no friction on these, we assume that these things aren't frictionless, that the entirety of the force is the impulse is in the normal direction between the two. If they were maybe they were rough onto each other, they could impart something in the normal direction because they'd be rubbing. But we pretend that there's actually, these are very, very smooth and frictionless. Remember, they're particles anyway, so that makes it a little bit more difficult for them to, because the shape and the size of them should not be influencing what the reaction are. All right, so like when people put English on a cue ball, right, that English can actually have some influence as to how the ball hits, because in reality the balls are not actually smooth, right? Here we go. Okay, so we draw the final momentum state right there. So here's the impulse and momentum diagram for this arrangement right here, and I think I'm going to show you here in a second that this right here is going to be equal to this, whereas this right here is equal to this, right? So the momentum before equals the momentum after of the individual balls. And do I show that? Okay, yes, I do. Okay, so here's what we do is that here is the impulse momentum applied to both particles treated together, but we can also have the particles treated individually, right? And I say normally, it's a pun. Typically, what we'll do, like in class 11, is we will treat them together as a system of both particles together in the impulse momentum, specifically so we could get rid of the impulse because it's equal and opposite. Remember, that's the reason why it's the conservation of momentum, is because there's an equal and opposite. But if we treat the thing as separate, right? There's another guy here. That's importing an impulse, but it's only in the normal direction. So if we treat this as an individual particle that's happening right here, right, and it's in the normal direction, we could take, in the tangential direction, we could take the sum of the moments that's taking place, and we notice that it's just going to be mass times velocity equal mass times velocity, but those are the same masses, right? So that mass is going to cancel out to each other, and so the conclusion is the velocity in the tangential direction before equals the velocity of the tangential direction after. And it also means it's in the same direction, right? So it moved, right? It had that velocity then, it has that same velocity afterwards in the tangential direction. And the same thing is true for the other ball, right? The other ball, we could take the impulse momentum diagram of the ball individually, and we're only doing it in the tangential direction. We can't do it in the normal direction when it's just a single ball because we don't know this impulse, but we can do it in the tangential direction. And so we have the momentum, initial state momentum equals final state momentum. And of course the mass cancels out, so the velocity before equals the velocity afterwards in the tangential direction. And once again, here's a summary of that impulse momentum diagram with both of the balls involved, right? So in the normal direction, what we will find is that we don't know this velocity and we don't know that velocity right here, right? So we don't know this velocity and we don't know this velocity right here. But we can find it because we can now use the coefficient of restitution to figure out as the second equation to be able to place out here. So here is a scenario here where we have a cue ball that's going to be cutting into this yellow ball. Is the yellow ball the one ball, I think? Anyway. So the cue ball actually, and I looked this up, is actually a slightly... yeah, it is the one ball, so that's why it's yellow. The cue ball has a little bit more mass, 0.17 kilograms, compared to the regular ball, 0.16 kilograms. And it's traveling at 1 meter per second on a felt pool table with negligible friction. And the angle between the balls is 45 degrees. The coefficient of restitution between the two balls is 0.9, and I looked that up. That's pretty accurate. And the velocity of each ball we want to find the velocity of each ball afterwards, and we want to know the magnitude and the angle with respect to the horizontal, right? We also would like to know the efficiency of the collision. So there's a number of things that we want to find out right here. So we want to draw this impulse and momentum diagram of this scenario right here where the ball, so that you can see that there's 45 degrees. And we're going to break down the initial velocity right here into components of 45 degrees. And we're going to be looking for the velocities in the normal direction after the fact, right? We might want to make sure that we don't scratch the cue ball, right? Something that we want to check out here. So we break out these into in components, and then we apply the conservation of momentum as a system of particles. And in the t direction, right? We know we already knew that the velocity, initial velocity in the tangential direction is going to be the initial velocity equal to, why is that 5 meters per second? I think that's incorrect right there. It must be a mistake. How did I manage that? All right, so there might be an error in this problem. It just jumped out at me. Oh my. Well, we'll have to have a second edition, won't we? Okay, and so this also in the tangential direction of the ball B, it was 0 to start with in the in the tangential direction, so it's 0 to start with, end with in the tangential direction. All right, so in the normal direction, we have we assume that there's going to be positive, right? So we don't actually know. The cue ball could bounce off and go backwards, but probably not. So we go ahead and we write out this equation right here by putting them in. And yes, so we have a second equation, right? So we have, no, that's in the normal direction. Yeah, so that's our first equation, I should say, right? That's our first equation. That's equation 1. Now we need another equation to be able to solve this. We use the coefficient of restitution. And we rearrange that by plugging the numbers in. We have a second equation. And so if we resolve those together, we solve them together, we get the, here is the final components right there. And okay, so what's good for me here, I believe, is that I went ahead and I used the correct value up here. Even though I had 5 accidentally up above, we did use 7.701. And so we're able to find what the resulting magnitude or speed of the final state of this is going to be the cue ball, right? And then this is going to be the ball, the one ball. Now these are magnitudes of the speed, but we would like to get these in rectangular components right here, right? So what we want to do is harken back to several classes ago. I think it might have been class 4, where we do a coordinate transformation, right? So we were, flashing back to here, which usually. There you go. Yeah, remember that these are the coordinate systems that we're using, and I even included it over here in this diagram right here. There's the coordinate axes that we're using for this, but we would rather be able to give our solution in terms of rectangular components. So we want to do a coordinate transformation, and so here is the vector of ball A, and here's the vector of ball B afterwards. So we go ahead and we use our coordinate transformation again to get it into the I, right? And then we're able to get it into the and the J. So here is the the vector in the rectangular coordinates. We already have the magnitude of that right there, and the magnitude better be the same thing as the magnitude here. But now we can have the angle, and this so we see that's going to be 49.13 degrees clockwise from horizontal, right? And then ball B, well, that's should be pretty. It should be at 45 degrees, and we do see that it's 45 degrees. But we went through the process anyway of doing the coordinate transformation and then finding the solution of the thing. Although this is an obvious result. So here is the total result right here. Here is the answer, and so you want to kind of picture how that's happening right there, and the direction that ball is going to go. And if we were somewhere in the middle of the table, we would be careful that trajectory would not send it into the other pocket in the other corner right there, because then we would scratch, and so if it was the 8 ball, we'd lose the game, right? Okay, so we want to figure out what the the efficiency of the thing is. So we take the energy and the initial state, right? And that's the total kinetic energy. Right? It's really just the kinetic energy of the cue ball A. There's no velocity of ball B. So we get 8.5 joules, right? Those are going to be, they could also be Newton meters. The potential energy is 0. The losses, the energy right there, the work that's going to have are going to be losses. The kinetic energy in the second state is going to be the total kinetic energy of both ball A and ball B. So we get like 8.108 joules. And so there's what that solution will be. We could also figure out the losses, but we could just as easily just divide the kinetic energy at state 2 divided by the kinetic energy at state 1, and we find that it's a 95.4% efficient collision that's taking place. So for more examples, go to the links below for Morgan and Claypool, and to find the part 1 and part 2 of the Engineering Dynamics course companion. And this, so far, we've just finished class 12, and that is the entirety of part 1. We're going to switch to part 2 in the next book, the next video, I should say. So it's the next book. Please consider subscribing to the channel, right? Many videos will be coming up. Newt, Dog, and Wormy are registered trademarks of someone named Edward James Deal.